The Hubble Space Telescope revolutionized our understanding of the cosmos, but Hubble was designed primarily for visible and ultraviolet light. To see the beginning of everything, we needed a new kind of eye. An eye that could see heat, an eye that could peer through cosmic dust, an eye that could detect light that left its source 13.5 billion years ago, when the universe was a mere infant. This is why the James Webb Space Telescope had to be built. This is why it had to be placed 1.5 million kilometers from Earth at a location called Lagrange Point 2, where it can keep its back permanently to the Sun, Earth, and Moon. This is why it needed a sunshield to keep it at temperatures colder than 200 degrees below 0 Celsius. At these temperatures, the telescope itself does not glow in infrared, allowing it to detect the faintest whispers of ancient light. The dream began in 1989, before Hubble even launched. Scientists at the Space Telescope Science Institute in Baltimore asked themselves what should come next. They knew Hubble would eventually fade. They knew infrared observations from space would require an entirely new architecture. The concepts they proposed seemed impossible. A telescope with a mirror 6 meters across. A cooling system that could maintain instruments at 7 degrees above absolute zero. A deployable structure that could survive launch folded up and then unfold perfectly in space. NASA approved the project in the late 1990s with an estimated cost of $1 billion and a launch date of 2007. What followed was a masterclass in how ambitious science collides with reality. The mirror design proved far more complex than anticipated. The original plan called for a single 8-meter mirror, but this was too large to fit inside any existing rocket. Engineers proposed a revolutionary solution: 18 hexagonal mirror segments that could fold for launch and then unfold and align themselves in space using actuators capable of adjustments smaller than a virus. Each segment is made of beryllium, an element chosen for its stability at extreme temperatures, coated with a layer of gold less than 1/1000th the thickness of a human hair to optimize infrared reflectivity. The sunshield presented its own nightmares. 5 layers of kapton, a material developed for space applications, each thinner than a human hair. The layers are separated by gaps that allow heat to radiate into space. The whole structure is roughly the size of a tennis court and must deploy through a sequence involving hundreds of moving parts, cables, and release mechanisms. Engineers built test after test on Earth, but Earth has gravity, space does not. They could only simulate so much. By 2005, the estimated cost had grown to $4.5 billion. By 2010, it exceeded $8 billion. In 2011, the House of Representatives proposed canceling the project entirely. The American Astronomical Society and scientific community rallied to save it. They argued that cancellation would waste the billions already spent and deprive humanity of discoveries that could reshape our understanding of existence. Congress relented, capping additional funding at $8 billion. The final price tag would reach nearly $10 billion. Delays mounted. The original 2007 launch date slipped to 2014, then to 2018, then to 2019, and finally to 2021. The COVID-19 pandemic forced further postponements. Engineers who began working on the telescope as young professionals found themselves approaching retirement still waiting for launch. The technical challenges were staggering. The 4 scientific instruments at the heart of the telescope required cooling to temperatures just above absolute zero. The near-infrared spectrograph alone contains nearly 250,000 tiny shutters that can open and close independently to capture light from specific objects while blocking out others. The mid-infrared instrument required a dedicated cryocooler because it needs to operate at just 7 degrees above absolute zero, far colder than the rest of the telescope. Testing consumed years. The entire telescope was placed in a vacuum chamber at Johnson Space Center that simulated the conditions of deep space. Engineers subjected every component to vibrations that mimicked rocket launch. They tested deployment sequences over and over, knowing that in space there would be no second attempts.